All right. So finally, applications of vectors. We use what we learned last time to solve some real-world problems here. All right, as we go through these, when it comes to navigation of airplanes, they measure from either clockwise from north. So we'll do it that way. We'll conform to the way it's set up. Of course, on our calculators, we've got to enter the equivalent angle in counterclockwise from the positive x-axis. So we'll do that, and then we have to convert it back. You may even have to holler at me and remind me to convert it back. We're getting the answer in terms of degrees clockwise from north. So when we get there, remind me. So number one, the wind is blowing at 20 miles per hour. So these are going to be miles per hour is a velocity, right? Miles per hour, it's a rate or a velocity. So these will be velocity vectors. Probably primarily what you've worked with probably all year in physics, velocity vectors. In the direction 330 degrees. So I'm working with degree measures measured counterclockwise from the positive x-axis. Sometimes even with wind, they'll talk about 30 degrees measured west from north or something like that, things like that. But we're going to just go ahead and convert it over. Express its velocity as a vector in terms of I and j. So the wind is blowing at 20 miles per hour in the direction 330 degrees. Let's go ahead and draw a picture here. Sometimes they'll say the wind is blowing from the direction of, and then in that case, the ray is actually, the vector is going in the 180 degrees in the opposite direction of where it's coming from. This says 20 miles per hour in the direction of 330 degrees. So 330 degrees is going to be all the way around, almost all the way around, but it's blowing right here. This would be the 330 degrees. And it's blowing at 20 miles per hour, so we just label this as 20. That's the magnitude or length of the vector. And so it says express its velocity as a vector in terms of I and j. So to do that, we're going to use what we learned yesterday. We've got the a part of the vector is equal to the magnitude 20 times cosine of 330 degrees, and b is equal to 20 sine of 330 degrees. When it's a special right angle, we can go ahead and find it in terms of radicals. If it's not a 30, 60, 45, one of those angles, then you have to use your calculator to find it. Probably in physics, you just type this into your calculator and get your decimal approximation. But we're going to find an exact value. It's good unit circle practice here. So right here, cosine of 330 would be what? Yeah, root 3 over 2. Good. And then sine of 330 would be 20 times negative 1/2. And so in terms of I and j, we have 10 root 3 in the I direction minus 10 in the j direction. So that is our vector in terms of I and j based on the magnitude and direction. So it's going one direction. I give you the magnitude and direction, you give me the vector in terms of I and j. And then you could write it in component form. It would be 10 root 3 comma 10. So, many different forms of the same thing. All right. We'll go the other direction. The rest of these examples are going the other direction. The more difficult direction is finding the vector in terms of magnitude and direction, and then adding them together, finding both two vectors, adding them together, getting that vector v plus w. We call that the resultant force, the sum of all forces acting on an object. So that's what we'll be focusing on today. Okay, so the sum of all forces acting on an object. These are interesting problems. So it says an object at the origin is acted upon by two forces. A 150-pound force makes an angle of 20 degrees with the positive x-axis. Maybe we'll stop and draw that. So a 150-pound force makes an angle of 20 degrees with the positive x-axis. 150-pound force. This is 20 degrees right here. While another force of 100 pounds is at 70 degrees. So another force of 100 pounds is at 70 degrees. So I need to write it up here. Not quite as long. As a matter of fact, it should be less than half the length of that one. So maybe right about here. So that's a force of 100 at 70 degrees, measured up from the x-axis. That's 100 pounds at 70 degrees. Find the direction and magnitude of the resultant force. So, resultant force means we're just going to add these two. Right? We're just going to add the two up. And so, if you think about what this would look like, I could either see 150 pounds force makes a 20-degree angle, and lots of x is 100 pounds. Say okay. So either way, this is the parallel principle. I could take this blue one and add it onto here, right? Or I could take the green one and add it onto here. Either way, I have a geometric description of adding the two forces, right? Now, if you think about what the resultant force will look like, I don't know that you necessarily need to add one onto the other, but if I do, just see if I can draw it here. We get a little parallelogram here. This is 100, and the resultant vector will be somewhere in between these two. Okay, so we're going to find this red one, and we'll call it V plus W, and we'll go ahead and find its direction and magnitude. So that's what my picture would look like. And the way we're going to go about doing that is by getting the two components. So the blue one, this is what you did at the very end. Yeah. Typically the origin is our starting point. It's just easier to make that like the center of where the forces are pulling from. So if you have, you're pulling, one person's pulling this way with a certain force, another one's pulling that way, where those two come together, it's easiest to make that the origin. Usually it is, yeah. Since we get to set our own axes, we might as well make the origin our starting point. And then really what this amounts to is that red vector I just drew, we're just finding its angle measurement, which is inverse tangent of the vertical side of it over the horizontal. And then that's the angle, and then we're finding the length of it, which is just the Pythagorean theorem of the vertical side squared plus the horizontal side squared, add them up, take the square root. That's what we're really doing. Now, without even worrying about what this coordinate is, we can do that by simply adding these two vectors, v plus w, together. And the way we're going to add them is the way we finished last time's lesson. So what we did in last time's lesson is we took each individual vector, wrote it out in magnitude direction form, converted it over to component form, and then just added the components to get our new vector. And then went back and used those components to get the angle and then the length or magnitude of it. Okay? So that's how we're going to go about it without having to worry about what is this actual end point right here so that I could use right triangle trig to find it. We don't need to worry about that if we know the other two vectors, and we do. Okay, so does that make sense? It's kind of, okay. If we knew what this coordinate was right here, I wouldn't even need to do the magnitude direction form of the green and the blue one. We're going to actually by changing them to magnitude direction form. So here's what it looks like. Let's take the blue one. And it's very formulaic, so it's pretty easy to do. But the blue one was the 150 at 20 degrees, right? So the two parts are 150 cosine 20 degrees in the I direction plus 150 sine of 20 degrees in the J direction. That's the blue one. That's vector V, if you will. And we're going to add that to what I have as the green one, which is vector W. And that one is 100 cosine of 70 degrees in the I direction plus 100 sine of 70 degrees in the J direction. And all we are doing to find the resultant vector is adding those two. Okay. So there's different ways you can do this, but probably the best way is just to do it the way we finished last time's lesson, is just go ahead and get something in terms of I and J, or even in component form, it doesn't matter, for V plus W. So V plus W equals, if you just find 150 cosine of 20, and we'll write this down this time. I'll actually just do all of this on my calculator, get the new resultant vector, and skip the intermediate step. But just so you see in your notes what's happening here. 150 cosine 20, what does that equal? What is it?
140.95.
Okay, so we have 140.95 in the I direction, plus, and then what's 150 sine of 20? $51.30, okay. 1.30 in the J. And then I'm going to add right below it, what's 100 cosine of 70?
34.20.
What was it, 30? 20. And then plus, with 100 sine of 70?
93.97.
J. And then you add these together. Like I said, you can do all this on your calculator and then just write your resultant vector. You can do the 150 cosine 20 plus 100 cosine 70. Those are the horizontal parts being added together, and then do it for the vertical parts. And what do we get here?
175.15.
Okay. Plus
145.97.
Okay. So then here's what I have. I kind of have a picture. At least I'm in the first quadrant, so I don't need to worry about the angle my calculator gives me when I'm in the first quadrant is going to be the correct angle. Remember, your calculator, the functional output it's going to give you for inverse tangent will be between here and here, in either the fourth quadrant or first. So if you're in the first or the fourth, whatever your calculator spits out is the correct angle. Now, if you have a picture where your resultant vector is in the second or third quadrant, you'll have to adjust that because your calculator is going to give you the equivalent value in one of these two. So you may have to add 180 to it. Okay? So the picture you need to draw. You need to do that. But here's all we need to do. We're going to find the norm of V plus W. And the norm of V plus W will be each of these squared, added up, take the square root. It'll look like this. Square root of 175.15 squared plus 145.27 squared. And so if somebody could calculate that for us. 227.55. And then you have to ask yourself, does that make sense in this problem? You know, what's going on here? It's being acted on by two forces. One is 100 pounds at 70 degrees, and then another one's 150 pounds at 20 degrees. They're both in the first quadrant, so it's going to give you a longer resultant vector than either of those individually, right? That makes sense. It's not like they're working in opposition to each other. So if they truly are, it's going to make it longer. You can see that in our geometric picture. Will it be that much longer? Does that make sense? No, I get, yeah, seems to make sense. But what would you estimate is the degree measure here? Something between what and what? Yeah, it's between 30 and 60, at least between 20 and 70, right? I think it's between 45 and 60. Okay. So a good guess might be it's going to be around 40, 45 degrees. That's probably a pretty good guess. Let's see. So we calculate the angle by saying theta is equal to inverse tangent of b over a, or y over x, or j over I, okay? The vertical over the horizontal. So, Nick, we've basically found the coordinates now. These are the coordinates of that red vector. So really all we're doing is right triangle mathematics on that. We're using the Pythagorean theorem to get the length of the hypotenuse of this right triangle. And we're using inverse tangent to get the angle that it is up from the positive x-axis. Okay? So 145.27 divided by 175.15 gives me an angle of, I think you're going to be right, it's going to be really close to 40 degrees. What is it? 39 points? Okay, good. There it is. So we've got a force of 227.55 pounds. At 39.67 degrees. So they're really working together for the most part. It's not like one's overlaying the other. That would be 250 pounds of force. So they counterbalance a little bit, but I was a little surprised that I had to look at mine to make sure the 227 was correct, because I was surprised it was that much longer, but it is. So. All right. Does that make sense intuitively, speaking in terms of the resultant vector and the degree measure it is? Okay. All right. Number 3. A 200-pound box lies on a ramp. Does anybody need more time on this? Copying this down. Got it? I need this whole picture in here. There we go. So a 200-pound box. There's my box right here. Lies on a ramp that makes an angle of 24 degrees with the horizontal. So it's the ramp that is a 24-degree angle with the horizontal. A rope is tied to the box from a post at the top of the ramp to keep its position. So a little deceiving on here. But this rope's tied off the box, so it's holding it up there to keep it in position. Ignoring friction, which, anyways, it makes it more complicated. There's always some friction there. But ignoring friction, theoretically speaking, how much force is being exerted on the rope by the box? So what we're trying to find out, it's the force being exerted on the rope by the box would be this little piece right here, x, represented by this little vector right here. So that's the x. So to do that, we're going to look at a couple different triangles here. If you look at, let me get my highlighter out here. I have some different colors. I think I used the color scheme here. I've got pink and I've got green. So that's the closest to pink I've got. So we're going to do the pink one first. So looking at and if you have two colors, it might be helpful here. This is how we're going to set up this problem. But if I take and highlight in pink here one of the triangles. Now, this triangle, I'm highlighting this one first because, one, I can figure out all the angles of this triangle. If I know that this bottom one right here is 24 degrees, and this is a right angle, you guys want colors? I can get... You're okay?
Actually, I'll put some.
Rachel can probably provide the whole class.
I forgot.
She's got it. She has a little suitcase. She just, I do. If anybody else wants some more colored pencils or anything here, just pass them around here. Ink pens, whatever. So, I think it'll be helpful to have. So we got this pink one here, 2490, and using our geometry here, blast from the past. What is this angle? Do you remember when this was the topic for the day? Finding the third angle. A little subtraction problem. Ooh, yeah, difficult, huh? 66 degrees. That's right. Because the sum of the angles of the triangle add up to 180. We know that's a right angle there. The reason I've highlighted the pink one there is because when this 200-pound box, when we say 200-pound box, if it were just hanging down due to gravity, it's 200 pounds is its weight due to gravity, it would be represented by this right here. This would be 200 right here. Right there would be 200, okay? So that right there would be 200. And so that's our little, we call it the pink one. So the pink triangle, we've got that top angle is 66. We know that that side opposite the 24-degree angle is 200, okay? And so we can use that information to go ahead and find out what x is. So take another color here. So let's get another color. And I'm going to connect, see, I have green is what I used next. But taking another color, let's go ahead and create another right triangle right here. Okay, remember, this angle up here is still 66. So I've still got, let's see if I can, I didn't want to highlight that. What I actually want to do is move it. There we go. So remember, this angle up in this corner right here, it's shared by both the pink and the green highlighted triangle, is 66. We've got the 200 right here, and then we've got x as part of this green triangle. Okay. So what I want to do is find out what x is there. So kind of a two-stage process here, but if I want to find out what x is, I know that we've got 200 here, we've got 66 here. Let's move this down. It's this whole thing now is 200 here, 66 here, we've got x here, and this time my right angle is right here. So we only use the only reason we used the pink one was to get that 66-degree angle. That's the only reason we used the pink right triangle, was to get that 66-degree angle, which is also used in the green triangle. So this green triangle has as one of the legs, the shortest leg, this value x that I want to find. So now what I've created here in this picture is a right triangle trig problem. Okay. So using right triangle trig, how can I solve for x? What setup would involve x? I could use lob signs, I think. Do I have enough angles? If I know what this angle is, yeah. You do. You could use a lob sign. That would work. Can I do it with just right triangle trig and avoid the whole law of sines thing? Sine of 24 equals opposite over hypotenuse. That would work as well. What's another way I could do it? Would tangent work? Opposite, nope, tangent wouldn't quite work. But cosine would work as well. So I could use law of sines to solve for x. I could use cosine, and I could use sine. We're going to set it up all three ways and you get it. And we'll get the same thing. So with law of sines, who suggested law of sines? What would that look like here? Okay, we know this is 24. Are we clear on why that's 24? Angles out up to 180 again. Okay, so you could sine of 24 over x equals what? Sine of 90 over 200, okay? I think that's a little bit of overkill. Here's why. What's sine of 90 equal to? 1. Okay. So if I set this up just using right triangle trig, here are the other two setups. I could say sine of 24 equals opposite x over hypotenuse 200. That's another way to set it up. Is that equivalent to what I have up here?
Yes.
Yes, because I could swap. Remember, sine of 90 is 1. We know that from our unit circle stuff. That would swap with the x, and I have it exactly this. I remember when we first did law of sines, we wanted to use law of sines even when they were right triangles. Is that okay? Yes. A little bit of an overkill. What's another setup here with cosine? Can you do it with cosine? If I'm at the 66-degree angle, what is x now? Opposite, adjacent, or hypotenuse? If I'm at the 66-degree angle, x is now the adjacent. So cosine of 66 degrees equals adjacent x over hypotenuse 200. So your choice. 3 different ways to set up the same problem. Go ahead and solve for x. See what you get. It agrees with what I have here. We use squiggly equals, round to the nearest hundredth. So it says, how much force is being exerted on the rope by the box? So that value x along the ramp, what is that force? That's what I got, 81.35 pounds. Yeah. And you should get the same thing no matter which method you use. So your choice. Any questions on that? Anything at all? And in physics, how would you have solved it? You know how to do it? Okay, so the 200-pound box. Remember, guys, the 200-pound box. That 200 pounds, the weight of the box has always got to be perpendicular to the ground. Okay, because it's gravity. So that's how I know this is 200. And then do you understand in terms of what I'm looking for here? X, okay. And X is part of this green triangle. I only use the pink one to get the 66-degree angle. That's the only reason I use it. To get the 66-degree angle. And then once you solve for X using that green one, you've got it. But 3 different ways to set it up. Not too bad to do. All right. These are always a little tricky, so just because of how it's measured. So we're measuring clockwise from due north. You got that? So clockwise from due north. We're going to translate that into counterclockwise from the positive x-axis because that's what your calculator is inputting and going to give you an output to go with. So an airplane is traveling 50 degrees with an airspeed of 300 miles per hour. So it's 50 degrees clockwise from due north. So here we go. I don't know what, you may need to put a star by it or write something next to this, but we're 50 degrees clockwise from due north. So that would be, yeah, you know where I'm headed already, yes. So 50 degrees here would be 40 degrees out from here, with an airspeed of 300. Airspeed of 300. So there it is. And then there is a 35 mile per hour wind coming from 120 degrees. Now it's coming from 120 degrees measured clockwise from due north. You with me? Yeah. Okay, so once again, the airplane's traveling at 50 degrees, measured clockwise from due north. So 50 degrees from due north is the same as 40 degrees up from the positive x-axis. When I go to plug this in to my calculator, I can't use the 50 degrees as the angle, right? My calculator is going to give me outputs based on the 40 degrees measured up from the x-axis, right? You with me? Somewhat? So if I want to know what, let's just work with this vector right here, the blue one. Let's call it v. Vector v is going to be, it's going to be 300 cosine of what angle? 40. It has to be 40. In the I direction plus 300 sine of 40 degrees in the j direction. So there it is. And I'll do my next vector in green here. It says there is a 35 mile per hour wind coming from 120 degrees. Now it's 120 degrees, I have it in red here, measured clockwise from north. So there's 90 degrees right there. 30 degrees farther down is my 120. It's coming from that direction, coming from 120. So, okay, here's 120. I'm just going to do a dashed line here. It's coming from that direction. So my wind, here's my wind blowing. We'll do a little wind here. It's blowing from the 120 degrees. So its actual measurement is what? Good. It's 150, yeah. Maybe I should. And this at least looks, it barely looks lower than. If I can rotate it. How's that? Is that better? Right there, maybe. So it's coming from 120 degrees. Remember, this is 120. There's 120 degrees, but it's blowing from that out that way. So the angle that I'm going to use for this guy, this is at 35. Oh, you know what else I should do? I like to make them kind of to scale if I can. So that is going to be, if that's 300, then 35 is going to look like about 10% of that. That's not 10%, but anyways, you get the idea. It's a lot shorter, right, the 35, because if 35 is representing the magnitude of the velocity vector, it's got to be shorter than the 300. With me so far? So we set at 150 degrees. So this is measuring from here. Measuring from here is 150 degrees. So when I go to write down my W vector, what do I write down? Yeah, it's 35. Good. Cosine of, it's not the 120, because if I tell it 120, the calculator thinks my vector is pointing up over here. This was 120, but this was equivalent to the 150 in terms of our mathematically speaking, on our calculator. So cosine 150 degrees I plus 35 sine of 150 degrees J. Then we're going to add the two together. So add these two together. I'll put a plus sign here. Move this 120 over. All right, so do you think you could add those two pieces for me? Just do 300 cosine 40. You can do it all in your calculator. 300 cosine 40 plus 35 cosine 150. Do it all together. It's a little more efficient than what we did in the previous example like this one. You'll get one value, round it to the nearest hundredth, and that's your I part of the resultant vector. I don't want to make any more of a mess of my picture, but what I'm going to do
is maybe you could either move the blue one over here or move the green one over here. Can you tell which quadrant we're going to be in based on my drawing? Can you tell? You think it's going to be in the first quadrant? I think it probably will. I think it may be in the first quadrant still, because that wind is so much shorter, it's not going to reach long enough to get into the second quadrant. See, right? See what happens. So what are these two components added up? What do you get? Oh, so it is moving into the second quadrant. It's negative what? You got negative 7.33.
I got 199.
That's what I got. I got 19. What did you do? 300 cosine 40, or even degree mode. Check that first. And then plus 35 cosine 150. I got 199.5 in the I direction. So I'm still in the first quadrant. This little guy right here is so short that it makes sense to me that it's still in the first quadrant, right? Relative to the 300 miles per hour that the plane's going, right? You got to figure it's like 10% of the line, right? So it's just adding on this little guy to the end of this. So we have this little guy added on to the end of this. So my resultant vector should be something like what I just drew in red. So plus, and then if you add 300 sine 40 plus 35 sine 150, what do you get? Yeah, 210.34 J. Okay. So then what our job to do here is now, okay, find V plus W, the magnitude of that, which is just square root of 199.5 squared plus 210.34 squared. Is that wind going to slow it down or speed it up? Slow it down a lot or a little, you think? Just a little, I would think, right? Is it going to change the direction a lot or a little? Just a little bit, yeah. So based on my picture, so what is the mileage or miles per hour here? We get 289.9 miles per hour. Okay, so it slowed it down a little bit. And then theta is equal to inverse tangent of what over what? Yeah, now, okay, we're going to talk about this here. 210.34 over 199.5. So we're going to get a theta that's measured up from the horizontal. Your air traffic control, and you give them the theta measured up from the horizontal, what's the problem going to be here?
Yeah, from north.
Yeah, you will be. Well, and you're not going to be very far off on this one because this angle is so close to 45 degrees, but we're going to be off nonetheless, right? So theta is equal to, and maybe you'll want to call this alpha, but I'm calling it theta because we've been calling theta the angle measured up from x-axis. We're going to call the actual angle they're looking for here, measured clockwise from north, as alpha. So theta is equal to what? 46.52, yeah. So the angle, or we could just call it the angle and not even call it a Greek letter. So the angle measured clockwise from due north is 90 degrees minus theta, which equals 43.58 degrees. So 90 minus 46.52, which equals 90 or 43.58. So then you can say, okay, the airplane is going 289.9 miles per hour at an angle of 43.58 degrees west of north, if you wanted to. Sometimes we'll describe it that way. 43.48, yes. 48. It's -1 for me. Good job. 0.48. Oh, brother. My degree marker is a little far removed. That's okay. Yes, Nick. For that figure, yeah. So we're in the problem, and that's what we're doing here is converting back to airplane language. But in the problem, it said the wind's coming from 120 degrees. So I went 120 degrees clockwise from north and landed 30 degrees below this positive x-axis. The wind's blowing from there, so it's going that direction. And so my vector is represented by this little green line here that is, well, if you think of this in terms of negative degrees, I'm at -30. So this is in 180 degrees the other direction. Add 180 to -30, and you get the 150. Or another way to think about it is, how many degrees am I down from here? 30, so I'm up 30 from here, which is 150. All right. You guys ready for the next one? So just the airplane ones, you'll have to finagle a little bit. Otherwise, you won't have to worry about it. It says number 5. Find the magnitude of the force required to keep a 3,500-pound car from sliding down a hill inclined at 5.5 degrees from the horizontal. So I'm just going to use that 5.5 degrees to find this angle up here. So this is what I would highlight in pink. This is my pink triangle. If I could do it, I don't know if that confused you or helped you. But so just looking at this triangle first, and noticing that if that's 5.5, this is 84.5. And then I'm going to take and find the green one here, which includes that 84.5. I should have drawn it bigger. There it is. There's my green one. It uses that 84.5. I don't know. There. It uses that 84.5. You guys see where the 90-degree angle is in the green one? Right here. And then it uses the force due to gravity is always this leg right here. And so right here, easier without all this. So the 5.5 gives me the 84.5 here. I draw this one here. There's my right angle, and I'm trying to find x right here. If that's 84.5, this is once again 5.5 degrees down here, and I have this piece right here, which is the hypotenuse of that triangle, is whatever the weight of the car is, which was 3,500, it looks like. So once again, you have multiple setups you could do here. The first question was, find the magnitude of the force required to keep a 3,500-pound car from sliding down the hill. So this is the same question as the previous one. So you can use cosine, sine, or log sines to solve it. Your choice. I set it up with cosine. So it's cosine of 84.5 equals x over 3,500. That's part A. So x is about equal to whatever 3,500 times cosine 84.5 is. Looks like it's about 335.46 pounds. So that's the force that it takes to keep that car sliding down the hill. Okay. So you better have a cable or something on it that can take that kind of force, 335 pounds, which is not much. That's not that bad. That ramp is helping. It's not that steep of a ramp, 5.5 degrees. And then B, it says on B to find the magnitude of the force of the car against the hill. So where is that in that triangle I just drew right here? Where is the force against the hill? It's this one right here, which is equivalent to this guy right here. So I've already drawn my triangle. Let's just label it Y, and you can translate that side length of the triangle over to the center of the car, which is the force that it takes to keep it against the hill. So in this case, I would probably use, if I'm using the 84.5 again, I would use sine. But once again, there's many ways you could set this up. But I would use sine of 84.5 equals opposite y over hypotenuse 3,500, and then solve for y. And when you solve for y, you get about 3483.89 pounds. There it is. So finding that force that would be acting on the car to keep it up the ramp, and then also that force coming straight down into the ramp to hold it down onto the ramp. Okay. So any questions on that one? Just added that part B is in addition to it. Adding the magnitude of the force of the car against the hill. All right, number 6. A river flows east to west. It's flowing east to west. I think I have a picture for that. It's flowing east to west. Okay. So there's the river flowing east to west. Any of you kayak? Any kayakers in here? No river kayakers? You heard of the term ferrying, when you ferry across the river? You have to figure that you're going to drift down the river, so you got to aim for a point, upriver. Okay. So, and if you miscalculate, you paddle like crazy. It helps you don't get sucked in and you start heading down where you don't want to go. But a river flows east to west. Now, this river is not going to be a problem because it's a slow-flowing river. It must be in the Midwest. A swimmer on the south bank wants to swim to a point directly north of her starting point. She can swim 2.8 miles per hour, and there is a 1 mile per hour current. What direction should she swim in relation to the south bank? So she's going to have to point somewhere over here. Okay. She's going to go point somewhere over here. Okay, the river's going at 1 mile per hour in that direction. You with me? 1 mile, slow going river. She can swim 2.8 miles per hour, and she's going to choose a theta so that she's actually going to hit the point directly across the river from her. So she's going to angle this way, swim at her 2.8 miles per hour, let that current take her down a little bit, and land right where she wants to. The width of the river? Not to get that angle theta, because I do have a right triangle. Right? And I have two lengths given to me. They're velocities, actually. They're not lengths, but lengths of the triangle. So what direction should she swim in relation to the south bank? So in other words, what direction, let's call it alpha, should she swim in relationship to the south bank, because I'm saying in relation to the south bank, so it's measured up from positive x. So you can find theta using right triangle trig. How would I find theta using right triangle trig? Inverse what? Opposite over hypotenuse. Inverse sine would work. Okay, so theta is equal to inverse sine of 1 over 2.8. What does that equal? That's not going to be my answer, but that's, what is it? 20.92? Okay, so the angle alpha that I labeled here, if we're measuring the angle measured from the south bank, which we would do that because we're treating it like the positive x-axis, then the angle, how did I word it on here? In relation to the south bank is alpha, I called it, equals 90 minus 20.92, which is 69.08 degrees. Okay. So that's it. Just the tip of the iceberg. Just a few problems that use that magnitude direction form. And yeah, I have 5 for you to try in groups. So if you want to, just go ahead and get into your assigned groups, please. I'll give you some time to work on it.